Hey everybody, it's Miss Smith. So today we're going to talk about wavelength and frequency and just kind of what that means in terms of, well, I like to use sound. We'll talk about light, here before too long. But we're going to kind of focus on sound a little bit so we all understand this. So I've got 4 different types of waves here, and so hopefully this kind of matches up with your notes that you've got. But I want to talk about, so we're still technically in topic question number 4, what is the anatomy of a transverse wave? But you're asked, you've got these 4 different waves, and you're asked to talk about these waves in terms of wavelength, in terms of amplitude, and in terms of frequency. And so it says to use very high, high, low, and very low. Okay, so let's look at this first one. So all 4 of these wavelengths have the same time period. So that's the reason why they're all the same length, is they both have the same time period. All 4 of these waves have the same time period. So you can see how things are very different in all 4 of these waves. So let's talk about wavelength. So this is in the same time period. This has a very low wavelength. Okay, so let's look at the next one. I have several waves in here. Now I do want to talk about how a wave is an up and a down. This is one wave. This is an up and a down. Okay, here's another wave, an up and a down. So that's 2 waves. And then an up and a down, up and a down. Okay, so it's 3, so this one's going to be like 3.5 technically is how many waves would be here. This is an up and a down. This is going to be like 1.5 or something like that. So it's up and a down and then like a half a 1. And then so we got 1, 2, 3, 4, 5. Okay, so there's a bunch on that one and there's a bunch on this one. Okay, so this one we've got still got a low wavelength. Excuse me. A low wavelength. Because if you look at the other 2, this has a high wavelength. And this one also has a high wavelength. Okay, so whether which one has very high, this is probably a very high wavelength actually, but it's got a lot of waves in that time period. But this one also has a lot of waves in that time period as well. So let's talk about in terms of amplitude. Now remember, amplitude is going to be how far you are from the crest to the origin, or to a trough to the origin. Okay, so this length right here. So on this first wave, it is a very low amplitude. Okay, now yesterday we talked about if you increase amplitude, you actually increase the volume. So if we're talking about sound, so if you increase amplitude, but this can also be said in another way. If you increase the amplitude, you increase the energy. Okay, so that's more of a scientific way of talking about it. Is that it increases increase amplitude, you increase the energy, because these waves have energy. We talked about that yesterday. It's a back and forth movement. Oscillation causes energy. That's what a wave is. So let's talk about amplitude in the second one. So this is a high amplitude. Okay, because look at the distance from the crest to the origin. That's very big on that one. This one also has a very high amplitude, so there's your origin there. So this will help a little bit. So this also has a high amplitude. And this one has a low amplitude. All right, now last one we're going to talk about is frequency. So frequency is how many waves I have in a time period. So remember, this one's only got like 1.5, so that's going to be very low frequency. And so this one's going to be high frequency. Well, I'm going to say, compared to the others, just say low. It's more like a medium, but let's say low frequency if we compare it to the others. Low frequency. This one here is a very high frequency, because it's about how many waves we've got. This one also is very high frequency. Okay, moving on. All right, so let's go on to topic question number 5. All right. So it says, what are the units used to measure wavelength, frequency, and a wave speed? What are the units used to measure wavelength, frequency, and a wave speed? So let me actually, I'm going to recolor this because I really should have done this in a different color. Okay, all right. So what are the units used to measure wavelength, frequency, and speed? So let's talk about wavelength first. So this one we talked about yesterday. Wavelength is literally the length of the wave. So we know that length is measured in meters. So now you may see this measured in meters, centimeters, millimeters, nanometers. It just really depends on what you're dealing with. So you may see it in meters, centimeters, nanometers, millimeters, any of those kind of things. It really just depends on if you're dealing with sound, if you're dealing with ocean waves, if you're dealing with different pitches of a piano. It just really depends on what you're dealing with. Light is normally measured in nanometers. So, but it's still a measure of length. But it is abbreviated by the Greek symbol lambda. Okay, and it's measured in meters. For the most part, it's going to be in meters. So we're going to talk about it in terms of meters. Okay, next one, let's talk about frequency. And this is going to be measured in what's known as Hertz. Okay, this is measured in Hertz. And so frequency is, the symbol is, let me back up, the symbol for frequency is a lowercase f, and it's measured in Hertz. Now a Hertz is a cycle per second. Okay, so it's actually, to be completely honest with you, it's just an inverted second. So you may see it written like this. That is technically a Hertz, because this cycle, this is an arbitrary unit. So really that's one of those units that can kind of disappear, and it doesn't really, it may be an oscillation, it may be a wave in the ocean, it may be a tone on a piano, it could be any of those things. So this is arbitrary. So that's the reason why you can see it written as an inverted second. So that's called Hertz. And Hertz is a cycle per second, or how many wave crests pass a certain point per second. Okay, it could be a wave crest, could be a wave trough. So frequency is a lowercase f, is measured in a unit called Hertz, or abbreviated Hz. Okay, let's talk about wave speed. So here's the formula you need for this, wave speed. All right, the speed or velocity. So the speed or velocity, which is the v, of a wave can be calculated using the wave equation. So that is a v, remember v stands for velocity, so wave speed, lambda times frequency. So the wave equation is written as velocity equals wavelength times frequency. The units for velocity are meters per second. That should sound familiar to you. All right, but it is wavelength times frequency. All right, topic question number 5. Oh, excuse me, number 6. Topic question number 6. What is the anatomy of a longitudinal wave? So yesterday we did the anatomy of a transversal wave. I feel like I said that right. Why am I thinking that's called something different? Transverse. No, I don't know why I'm saying transversal. I was thinking longitudinal. Sorry. So transverse wave. So what is the anatomy of a longitudinal wave? What is the anatomy of a longitudinal wave? Okay, so remember, this is the one where you've got, like a spring, and then it's like bunched up in one area, and then it, goes out, and then it's bunched up at another area, and then it goes out. So where it is close together like that, that is called a compression. We talked about this a little bit yesterday. That is a compression. That is a high pressure area. particles of the wave crowd together. Okay, so now this, I want you to realize that this is actually just a, what's the word I'm looking for? This is just a model. So this will be like a slinky, and one person will be holding it over here, one person will be holding it here, and we've got motion moving in the horizontal direction. So when we did transverse wave, we had somebody moving the motion in a vertical direction. This is in the horizontal direction, like this. Now, what I actually want to point out is this would actually be like a tube of air. And so, and the particles within the tube would actually like bunch up around this area and then spread out over here, and then bunch up here, and then spread out over here. And eventually, these areas that would bunch up would actually move up and down the tube like this. Where the parts of the wave is spread apart, that is called a rarefaction. So this is a low pressure area. So this is where the particles of the waves are spread apart. Okay, so the wavelength for this one, it says the wavelength is the distance from the end of one compression is the distance from the end of one compression, or from the end of one rarefaction to the end of the next rarefaction. The amplitude, so that's wavelength. The amplitude is the change in pressure between the rarefaction and compression points. Okay, the higher the amplitude, the more energy the wave has. We've talked about that a little bit already. Label where the compressions are and where the rarefactions are. So these are going to be your rarefactions where they are separate, and these are going to be your compressions. Okay, this is also a compression. You have a rarefaction here and also a rarefaction there. And so the last thing we're going to talk about is, this is in topic question number 7. And so this one says, what is a surface wave? Now we've been talking about sound a little bit, but what about waves in the ocean? What is a surface wave? So, it's got this picture of these ducks on here. It says a surface wave is another type of a mechanical wave. That occurs in water. Particles move both parallel, I'm going to use the symbol for parallel, and perpendicular. There's a symbol for perpendicular to the motion of the wave and their motion becomes circular. So the example, oh, I spelled that wrong. So the example that it gives is actually a duck sitting on water, like a little rubber duck. And it looks like I'm still spelling it wrong. It looks like the duck's almost going in circles, but that's because you have transverse and longitudinal waves. You got perpendicular and parallel at the same time. So the duck's position does not change, but as the surface passes beneath it. So the duck's position doesn't change as the surface wave passes beneath it. So the duck kind of stays there, but it's because you've got your parallel and your perpendicular. So, and there's a big arrow in there, and so that to fill in that arrow is just the wave direction. Okay, last thing we're going to talk about is surface waves a little bit more, and then we will be done. So ocean waves are a type of surface wave created by wind. Energy is moving through water, but the water particles themselves are traveling in circular paths. And so again, this is because of the parallel and perpendicular waves at the same time. The wave motion changes when the wave hits the shore, and surfers take advantage of this before it collapses. And so it says the wave motion changes when the waves hit the shore. Surfers take advantage of the waves collapsing. So that's it for today. If you have any questions or if I missed something, let me know.